welcome back from spring break. Hopefully you guys had some rest. Just a couple things before we get started here. We're going to have quite a few of these videos that come through, so make sure you watch them. I'll do my best to explain things clearly and slowly. We are going to work through the rest of the stoichiometry unit and then head into gas laws. As you've seen, there's been changes to the schedule. I'll talk about that at a little bit later time in a separate video. But I just want to encourage you, these last two units are really critical for you to understand, especially if you're going into AP chemistry or physics or AP physics. Okay, they contain a lot of math components for future science classes. So we're kind of stripping them down to their bare bones of what you need for those future classes. So please make sure that you are following along and you understand. As always, I'm available via Remind or also through Google Classroom, or just school email is fine as well. There's also lots of videos that are available if you need additional practice. Okay, anytime you see a worksheet like this, you can basically Google our title here, and that will bring you to a whole bunch of different other examples of the same thing. Okay, so let's dive into this. I'm going to do a couple examples on here, try and keep it as short as possible. If you need to, don't understand something, the great thing about this format is that you can go back and rewatch it. Okay, so if you don't understand this after the first fly through, okay, pause the video or go back and watch it again. Okay, so we're talking about this thing called empirical and molecular formula. And what is, most of the time we've been using the molecular formula. And the molecular formula is how we find it in nature. And basically what that means is this, okay? When we're looking at a formula, here's an example, H2O2, right? This is hydrogen peroxide. The empirical formula is the reduced version of that, okay? So notice that this is two hydrogens and 2 oxygens. The empirical formula is going to be the lowest basic ratio, okay? Lowest basic ratio between the two. So here I actually have some examples that are written, and these are all written as molecular formulas, okay? So what we're going to do is we're going to take these and we're going to reduce them from the molecular formula into the empirical formula. So we're going to do this, right? Okay, write the empirical formulas, okay? So this is just a bunch of reducing, basically. So we're going to take a look at this one. We got P4O6. And because these are both even numbers, I can divide this by 2. If I divide this by 2, the 4 reduces to a 2. The 6 divided by 2 is 3. So the empirical formula for this one is P2O3. Okay? This is my molecular, how we find it in nature, and this is the reduced version. All right? Let's do this one over here. Okay, 6 and 9. I'm going to divide this one both by 2, and I get C3. Nope, I can't do that. 2 is not going to go into my 9. How about I divide by 3? 3 goes into 6 2 times, and 3 goes into 9 3 times. So I'm reducing this to C2H3. Okay? So the molecular formula, that's going to be the larger number. Okay, it will be the one that we find in nature. The empirical formula is going to be the reduced version of it. Okay, I do want to give one other example on here. So, for example, something like this, H2O. This is the empirical, and it's also the molecular. Okay, so sometimes the empirical and the molecular match up, so we'll have the same thing. I can't reduce this any further. Okay, we have to have whole numbers here. I can't have that as a fraction, right? So here's an example of this, the empirical and the molecular both match up here. Okay. I'm going to do one more on here and then leave the rest for homework. So let's take a look at this kind of hot mess here. The best thing to do here is to actually combine all of our elements. So I'm going to combine the carbons first. So C2, I like to cross them out so I know what I'm doing, I'm keeping track of what I've already accounted for. H2 plus another H, that's 3 H's, plus another 2 H's, that's 5, plus the last one here is 6, so H6. And oxygen, O2. Okay, so I counted up all these and I put them in a much more simpler form here. And it looks like I've got 2, 6, 2. I can easily divide this and reduce it by a factor of 2. So that brings me to CH3O. Okay, so this is my original molecular, and this is my reduced or lowest basic ratio of CH3O. Okay, so that's some basics on what the difference is between a molecular formula and an empirical formula. Okay, and we can switch between the two. Okay. The next thing we want to do is we're going to look at how do we calculate the empirical formula. Okay, the empirical formula is usually where we start. We'll deal with how do we calculate the molecular formula in a later lesson. Okay, so we're going to take a look at the empirical formula, and this is going to give us, we're going to do it two ways. Okay, they're really similar. Okay, it just depends on how the problem is worded. And the first one here, by the way, this is kind of a step-by-step of what I'm going to walk you through. I'm not going to read it to you. You can read it to yourself. But I am going to walk you through this problem here, okay? So this is asking us to calculate the empirical formula of a compound for a sample that contains 7.808 grams of carbon and 92.192 grams of chlorine, right? And we want to come up with the formula. Well, I can't do it from looking at the mass, okay? Because all elements have a different mass number, okay? So these are not equal in the number of molecules or atoms or moles that I have between the two of them. Okay, so what I'm going to do is I first need to take these and determine how many moles of each I have. All right, so I'm going to take the first one. I'm going to look at carbon. So 77.8088 okay, grams. And I'm going to put below this the chlorine. 92.192 grams, all right? Now I'm going to divide this by the molar mass, okay? Molar mass coming off the periodic table is 12.01. And this is going to give me how many moles of this I have. And I get, get 0.6501 moles. Okay, now sig figs aren't super important here, but it is important that we write this out to like 4 or 5 digits. Okay, you'll see why in a minute why we need to have some rolling numbers here. Okay, but we don't have to write the whole thing out. Here's the extended number. Okay. I went to the first 4 digits on this one. That's usually good enough. Okay, and then we're going to divide this by the molar mass of chlorine, which is 35.45 grams. All right, and this gives us 2.600 moles. Okay, so this is the moles of carbon to moles of chlorine ratio. Okay, so I have 0.65 moles of carbon. I've got 2.6 moles of chlorine. This is a little bit helpful because it shows that I'm going to have more chlorine than I am carbon. But when we write formulas, they have to be in whole numbers. So there's an easy trick to get that. Okay, and what it is we look at the 2 we have, or 3 or 4, and we find the smallest one. In this case, we have the fewer number of moles of carbon at 0.6501. I'm going to take this and I'm going to divide both by the smallest quantity. All right. this is easy math, okay? So 0.6501 divided by itself is 1, all right? And when I do this, all right, I get 2.5. So we're getting closer to the empirical formula, all right? However, I can't write this as C1 Cl 2.5, right? I need to bring these both into whole numbers. So what can I multiply this entire thing by to make these whole numbers? Well, this is already a whole number. You don't have to worry about that. But this is 2.5. So the easiest way to do that is to multiply this whole thing by a 2. When I do that, we end up with C2 Cl5. Okay, and this is your empirical formula. Okay, and we're going to abbreviate it with an EF for homework's sake. Okay, that's our empirical formula. Okay, so take a look at this. That's the one way we do that. Watch it again if you need to. There's a bunch of practice problems on the back of this sheet. Should help you out. The second one I want to look at sets up a little bit differently. Notice this one, okay, has grams of carbon and chlorine. When we have this down here, right, this is 43.4% of sodium, 11.3% carbon, and 45.3 of the oxygen by mass. Okay, so this is a little bit different because we're starting with percentages. Now, the cool thing about this is if you notice, all of these add up to 100. Okay, so if I take 43.4% and I choose a sample of 100 grams, this is going to end up giving me 43.4 grams. So we can convert these percentages into grams if we assume we have a 100-gram sample. So 100-gram sample, what is 43.4% of a 100-gram sample? Well, it's going to be 43.4 grams of Na. Okay, and then I've got my carbon. Here's my carbon, and here's my oxygen. All right, so my carbon, I've got 11.3 grams, and my oxygen, I have 45.3 grams. Okay, now at this point, this problem starts to look a lot like what I did in example 1. All right, I've converted my percentages into mass, okay, by using the 100-gram sample. All of these will add up to that 100 grams, all right? And now I'm going to divide them by the molar mass. Okay, so Na, its molar mass is 22.9 grams. Carbon's molar mass is 12.01 grams. And oxygen is 16.00. Okay, what this step does, just like I did in example 1, is this is going to give me how many moles of Na I have, how many moles of carbon I have, and how many moles of oxygen I have. And then I can, from there, determine what my empirical formula is. All right, so let me do the calculations on here. This is 1.8951. This is 0.94088. And this is 2.8312. All right. 4 or 5 digits are usually good enough here. Okay. We're not using sig figs with this type of process. So I want to find the smallest one. I'm going to divide all 3 of these by the smallest one. If you haven't picked it out yet, yep, it's going to be this one right here, carbon. All right, so that's easy one, 0.94088. That's going to equal 1. This one is 0.94088. This equals 2.014. This one equals 3.009. Now, if you notice, we do not have a perfect value here. Okay, look, we've got some values that are in the thousandths and hundredths spot. Okay, so what we're going to do, what we're looking at, is we're really looking for what this looks like at the 10th spot. Okay, I want to make sure that like this is really close to a whole number. So this is 2, this is 1, this is 3, right? So Na2C1O3. Okay, and this is our empirical formula. Okay, so that's example number 2. I want to show you example number 3. I already worked that out. I'm just going to show you that this is okay because some of you are going to be like, what? All right. So here's number 3 in the example category. Okay. So this one gave me 1.43, and this one gave me 1.4346. We're going to call that close enough, and this is a one-to-one. Sometimes you will have one-to-one empirical formulas. Okay. So that's close enough for that value to stick. All right. So there you go. Have fun with that. If you have any questions, you can email me. Other than that, have a great day. Talk to you guys soon.